This is the 8th video for IB Astrophysics. We're going to be looking at a very important topic, which is how do we know how far away stars are? A lot of the discussion we've had so far centers around knowing how far away a star is. But how do we figure that out? Well, it turns out that the simplest way to determine how far a star is a method called parallax, which is based on the fact that as the Earth goes around the Sun, it's moving, of course, and that means that the apparent position of the stars changes ever so slightly over the course of a year. So what you do first is you measure the angle to a star in January. Then what you do is you make the same measurement again 6 months later, so January to July. We define half of that difference as the parallax angle. And the way this looks in the diagram, you've got the star up here, and the distance of the Earth to the Sun is 1 AU, and you have what is essentially a right triangle with parallax angle P and the distance the star from the Earth, which is D. Now, trigonometry would say that sine of the parallax angle equals 1 AU over D, but because P is so very small, sine of P is approximately equal to P, and you get P equals 1 over D. The units there, if P is in radians, then D would be in AU. But we typically will use different units. P is usually measured in arc seconds. Now, 1 arc second is a tremendously small angle. There are 60 arc minutes in a degree and 60 arc seconds in an arc minute. So 1 arc second is 1/3600th of a degree. And given that the closest stars have parallax angles of less than 1 arc second, we're talking very, very small angles. So typically P will be measured in arc seconds. And then if we use P equals 1 over D, D is measured in parsecs, or per arc seconds, hence the name. And that's why we have the unit of parsec and kind of where the name comes from. You need to remember P equals 1 over D. You also need to be able to reproduce this diagram and explain how parallax angle is measured. Oh, here we go. Repeating this again, D equals 1 over P if P is measured in arc seconds and D is measured in parsecs. Notice that the farther away the star is, the smaller the parallax angle is. So if we've got a star that has a parallax angle of 0.04 arc seconds, 1 over 0.04 is equal to 25 parsecs, which is, if we do the conversion to light years, 81.5 light years away. If you doubled the distance, you would cut the parallax angle in half. Now, parallax is a very useful technique, but it is highly limited. First off, the Earth's atmosphere, which introduces distortions equal to about 1/100th of an arc second. And that's basically what twinkling is. Stars twinkle, they appear to move a little bit. It's due to the light going through the atmosphere and getting distorted. The result is that from Earth, you can't really measure parallax angles less than at 1/100th of an arc second. And that means you can't really measure the distance to stars that are more than 100 parsecs away. It's 300 or so light years. You can sort of get around this by using orbiting satellites. Orbiting telescopes can measure parallax angles down to about 0.005 arc seconds. And so with the I forget what the name of it was, but there are some satellites that have gotten parallax measurements to most of the stars in our neighborhood within several thousand parsecs away. Now the other limitation, and this is not something IB is going to ask you about on the test, but it's kind of interesting, is that red supergiants have luminosities that don't stay the same. They change, and they don't always change in a predictable fashion. And they have its asymmetrical pulsation, so that sometimes the left side of the star is where most of the light's coming from, and sometimes the right side of the star is where most of the light's coming from. The result is that for these stars, it's difficult to compare observations that are made 6 months apart. Result is, we're still not totally sure how far away some of the very bright stars like Betelgeuse are. No one really knows how far away Betelgeuse is. That's one of the interesting facts of astronomy. But there's another way that we can measure distance to stars. It's called spectroscopic parallax. And despite the name, it is not in fact parallax. It is used for measuring distance, but it is not in any way like parallax. In spectroscopic parallax, what you're doing is it works for main sequence stars. If you look at the Hertzsprung-Russell diagram, if you know that a star is main sequence, and you know its spectral class, you can get a pretty good idea of its luminosity. So what you do is, the first thing you do in spectroscopic parallax is you look at the spectrum and ask, okay, what's the peak wavelength? Then what you do is you calculate the temperature using Wien's displacement law. T equals 2.9 times 10 to the minus 3 Kelvin meters divided by 5.1 times 10 to the minus 7 meters is the wavelength in this case. And we find that this star has a surface temperature of about 5,700 kelvins. Now what we do is we look at the Hertzsprung-Russell diagram and figure out about what its luminosity is. And looking at it in your book, this is on page 349, Hertzsprung-Russell diagram indicates that the luminosity of this star is going to be approximately twice the luminosity of the sun, which is 7.8 times 10 to the 26 watts. Now that you know the luminosity, you can measure the brightness and use it to calculate the distance. Remember, brightness equals luminosity over 4 pi d squared, which means that d is equal to L over 4 pi b square root. Times b in this case is 1.8 times 10 to the minus 13 watts per square meter. Plug the numbers into the calculator. And we find that this star is 1.86 times 10 to the 19 meters away, which is equal to about 1960 light years. So if you know, once you have the Hertzsprung-Russell diagram populated, you can figure out pretty much what the distance to almost any main sequence star is. And this is useful for distances up to about 10 megaparsecs. It's about 3 million light years. That means that it's useful for determining distances to almost any star in the Milky Way galaxy. Now there are some obvious limitations here. The biggest one is that the Hertzsprung-Russell diagram, the luminosity values for a particular temperature are spread out over almost an order of magnitude. So that means that your luminosity numbers are really, you could be off by almost a factor of 10. And that means your distance values, which goes the square root of the luminosity, could be off by a factor of 3, which is not great, but for astronomy we say that's okay because we don't have a lot of alternatives. So what you need to know is how parallax works, be able to explain it, what kind of measurements are made, how the calculations are done, know what an arcsecond is, know what a parsec is, and you need to know what spectroscopic parallax is too, and given brightness and maximum wavelength, be able to calculate the distance to the star using that method.